we will discuss about the variance of resistivity with temperature. And okay, thanks to all of you to show up in such large numbers. I was not expecting. Let's start with. I'm starting with insulators. So we are doing in order of increasing conductivity or decreasing resistivity in general.
पर लार्ज नहीं है.
Yeah, so before I go to insulators, so what are insulators? Basically insulators which are very bad conductor of electricity or which does not conduct electricity at all in normal conditions. So before going to insulators, I will be discussing a theory which is known as band theory. I think that we have somewhat studied it in class 12 when you are learning about semiconductors. So let's assume an atom. Okay, let's suppose this is an atom, and if we try to represent the various energy levels of that atom. So let's suppose this is the increase. The energy level is increasing from bottom to top, and this is the 1s orbital. This is 2s. This is 2p. We all know that for a single atom, the energy level will be like this. Okay. But what if there are two atoms which are very close to each other? So when there are two atoms very close to each other, if there are ions, they will form ionic bond, and if there are some other kinds of atoms, they can form covalent bond, and there are metallic atoms, they can also form metallic bonds. Okay, so basically they will form bonds. How they form bonds? So basically these two atoms together will call as a molecule, and the orbitals of both of these atoms having similar energy levels will overlap each other to form molecular orbitals, as we all know. So let's suppose these are the molecular orbitals. This is 1s, this is 1s star, this is 2s, this is 2s star, and this is 2p, and so on. Okay, we all know that. So for two atoms, we have two discrete energy level for a single orbital, and if we keep on increasing the number of atoms, let's suppose 3 atoms will have 3 discrete energy levels which are very close to each other. Okay, the energy difference between them is too low. So this is 1s star, this is 1s double star. So conventionally when you're talking about a molecule, we will talk about bonding orbitals and anti-bonding orbitals, but in this case, it's not exactly bonding and anti-bonding. Electrons prefer to stay in bonding orbitals because it has lower energy. It happens due to the constructive interference of the probability density function. So it's the constructive interference, and this is the destructive interference. Okay, so it will have higher energy, and the constructive interference will have the lower energy. So similarly, it will happen with 3 electrons. The orbitals they will interact with each other, the similar orbitals of these 3 atoms, and they will form 3 discrete energy levels. So then it will also happen for 2s, let's suppose 2s star, 2s double star, and if we keep doing it for n number of atoms, let's suppose we will have n number of discrete energy levels. Okay, and they will be very close to each other. N number means you can say there are many atoms that are close to each other. Okay, and practically the energies in between are so little that the discrete lines are basically indistinguishable to each other. So what it appears to us like a energy band. Okay, and what happens is that these there will be different energy bands, and the lowest energy band we will call is the valence band, as we all know. Sometimes we also call it the bonding band, we also have the valence band, and the higher energy will be the conduction band. This entire thing is also known called as the linear combination of atomic orbitals. Okay. So again, electrons will prefer to stay in this valence band, and they will only go to the conduction band if there is enough energy provided to them. Okay. So these are their electrons. So what happened in materials, if we are talking in terms of conductors or insulators or semiconductors? In conductors, these valence band and conduction band are overlapping with each other. So the electrons actually do not need any additional energy to go to the conduction band. They can freely move to the conduction band and they can conduct electricity very easily. In semiconductors, there is a gap, but the gap can be overcome if we provide energy to the electrons. But in in case of insulators, yes. So in case of insulators, what happens is that the gap between the two bands is too large. What do you mean by too large is conventionally say that it's greater than 4 to 5 electron volt. Okay, so electrons will stay in here, and this gap is known as the forbidden gap. Why forbidden gap is there or why it occurs, it will be explained by my colleague Agastya in 2 minutes. So this is the conduction band, this is the valence band. So in case of insulators, the forbidden gap is too large. So the electrons face difficulty to move from valence band to conduction band. That's why insulators can conduct electricity pretty efficiently, and they are very bad conductors because they have very less number of charge carriers. Okay. Then, so when we increase the temperature, okay, when we give temperature to the electrons, basically we are trying to give energy to the system, to the entire system. So the electrons will gain kinetic energy. So this we are talking at ideal case, which is T is equal to 0 Kelvin, where the insulator's resistivity is basically at infinity. But once we start increasing the temperature a bit, let's suppose T is equal to some Kelvin. Okay, we have increased the temperature. So now what will happen? Some of these electrons that are in the valence band will start going to the conduction band. Okay, in the conduction band, so the resistivity will start to decrease and it will start to conduct some electricity. Still, even at room temperature, the insulators can conduct electricity pretty well because the number of electrons that are jumping to the conduction band or promoting to the conduction band is still very low. Okay. So what will happen if we keep on increasing the temperature? That's why we have to steady. So if we keep on increasing the temperature, there will be a exponential decrease in the resistivity of the insulator. Okay, but why is there a exponential resistivity? I will explain in a bit. So we know that conductivity is equal to number of charge carriers multiplied by charge on an electron multiplied by mobility of the electron. So resistivity should be equal to 1 by n e mu. Okay. So from this equation we can deduce that resistivity is proportional to inversely proportional to number of charge carriers. Okay. So I want to introduce a new term that I am not very knowledgeable about. That is that n is proportional to the Boltzmann factor, which is e to the power minus Eg by 2 kT. this term will be also explained by my colleague Agastya here. He will explain it in a bit because it's very prominent in explaining semiconductors. Okay, so this is the Boltzmann factor. Okay. So from here we can replace this because this is proportionality. We can efficiently replace n. We give it the minus e by 2 kT. Okay, I forgot to explain what is Eg. Eg is the energy gap, that is the forbidden gap I have mentioned there, and K is the Boltzmann constant, T is the temperature at which we are measuring the resistivity. So resistivity is proportional to 1 over e to the power minus Eg by 2 kT, and we can write it as rho is proportional to e to the power Eg by kT. I just wrote the denominator in the middle. Okay, and to remove the proportionality, we will add a constant which is rho is equal to rho naught, which is the like a base resistivity with a reference resistivity e into e to the power Eg by 2 kT. But now we just discussed that it will decrease exponentially, but this is a positive term. But then how it will happen? So see, if we increase the temperature, this term Eg by 2 kT will decrease because T is in the denominator. Okay, so if this decreases, e to the power Eg by 2 kT also decreases. So that's why it is a decreasing function. So if you try to plot it in a graph, okay, I draw it here. This is resistivity in y-axis and temperature in x-axis. So it's the exponential curve. It will decrease like this, but it will not like go on forever. Okay, it will not decrease forever. It will not approach x-axis because what will happen at a certain point, if we keep on increasing the temperature, there will be a breakdown point of the material. Okay, there will be breakdown point of the material. Then what will happen? It will catastrophically start conducting, and it will be non-linear decrease in the resistivity. Okay. But what will happen if we further keep on increasing the temperature more and more? The material basically will get destroyed because most of the insulators can sustain at high temperature. What happens with metal is that they melt and they can retain their chemical and physical properties after that. But what happens to insulator? Once we give them more and more thermal energy, they will there will be a change in their chemical and physical properties. So they will not show the resistivity if we ever even cool them after this experiment or whatever we have done here. Okay, so from all of these we can conclude that coefficient of resistivity, which is known as alpha, okay, it is negative for insulators. Okay, coefficient of resistivity is negative for insulators. That means if we keep on increasing the temperature, the resistivity will decrease, and yeah, that's what it's all about. Thank you. Yeah, 2-3 questions. Any doubts?
Can you explain the conductance band a little bit more? Like, is it a part of the atomic system or is it like above it?
See, the conduction band forms because of there are like if you take a lattice, it's actually a lattice of atoms. Okay, so there will be multiple atoms and they will have their own energy levels and orbitals, and they will kind of overlap each other because it's quantum mechanics. It's all waves. As much as I know, there will be a wave property of the electrons. So these electrons will have constructive and destructive interference, and according to that, if the conduction band and the valence band will form. Okay, for different materials, it changes. Okay, like for some materials, the destructive and constructive difference they don't have a very big difference. But for insulators, yeah, there is a very huge gap. That's why it's very difficult for these electrons to move to the conduction band.
In case of superconductors, then where they overlap. Okay, fine. That's not even. Never mind.
Superconductors, that my colleague Divyansh will explain. Yeah. Any more questions? Yeah.
Can you repeat the alpha things? Like what was it? Temperature coefficient?
Yeah, that is the coefficient of resistivity. So in terms of conductors, resistivity of conductors, we have learned that rho is equal to rho naught 1 plus alpha T minus T naught. So it's basically the same term, but here it tells us that the resistivity increases linearly as a function of temperature. So it's for conductors, it's not for insulators. But yeah, it's the same coefficient of resistivity. So it's for conductors positive, for insulators and semiconductors negative. Yeah. Louder, please. At the breakdown temperature, what happens is that suddenly, like basically the electrons and the nuclei, they will rip apart. Okay, they're getting too much energy. So what happens? They will start conducting more and more. Okay, they will start behaving like conductors. Okay, but they're not exactly conductors, because soon enough the material itself will get destroyed. So we can achieve breakdown point in insulators through various methods, like providing high potential difference. We can also do that, but in this case we're doing it using, like, giving thermal energy continuously.
So you're basically saying that the material is destroyed, which means the molecule rips apart and the atoms become separate.
See, it depends on the insulator. Maybe the insulator gets oxidized, or it will just burn out. There is a term called like carbonization. It will carbonize. Okay, so it cannot retain its original properties after that. Okay.
So essentially
Okay,
it undergoes...
we can discuss after class. Thank you.